So, second part. Now I'm switching to talk about big data. And we now looked at different computer systems and ways to process this big data. But what does it mean to have big data? And I've already mentioned these velocity, volume, and variety. And usually we need, when we have this amount of data, we need to have a performant system, both hardware and software, which is scalable and flexible. And you're ready for handling big data when the scaling is not scary. So it's your code and your system can handle 10 examples, 100, and 1,000 examples with the same amount of effort from your side, or more or less. Takes a little bit more administration, I believe. But in principle, the code itself shouldn't care much about if you have more and more data. It just takes longer. So, of course, time can be an issue, but that is not the big thing. And another thing is when you starve for enough data, it's question if it's good or bad. But when we're talking about AMPLab, that's big machine learning, big data laboratory, and for them, it's always the limiting factor, having enough data. There are different sides of it, and I think they are on the big side. There are also the other side that you don't have enough data because there are not enough samples. So say you do some experiment with limited beam time and you can only produce, say, 5 examples, and that's not always sufficient to produce reliable methods. But so sometimes you are starving because you really don't have a lot of data. But in other cases, you're starving because you need so much variety in different ways. So it's a little bit double-sided on which end you starve. And important is also there are no clicks per sample. So you want to minimize your interaction as much as possible. So of course you have some interaction in the beginning where you set the basic parameters of your processing. But after that, you're not supposed to go and click in every image. Clicking in every image works for 10 images. 100 is questionable. 1,000, no way. So you really want to minimize the number of clicks you need on the individual samples. And during the main processing. Of course, you can have some clicking around for the parameterization, but after that, it should be okay. And there are ways to handle these large data, and this is a little bit simplified story about the big data problem that Google ran into many years ago. And they have really huge amount of data. So they have peta and exabytes of websites, and they want to collect information that makes sense from all these in order to be able to indexing and searching quickly. I mean, today you do a Google search and it's done in some, say, 100 milliseconds, and you have already thousands of hits, which is quite impressive actually, that you can get that information in so short time. And what Google is using is something called PageRank, an algorithm that they have developed to evaluate the quality of different websites. And in principle, what they need to do is, for every website out there, and that's quite many, they want to run some kind of PageRank function on the current site. This includes how many links there are, where the links are going in many steps, and they want to analyze this. And one idea would just to be splitting this long list of websites that they know of into a bunch of groups and then have every computer run its group and done. Now, with those amounts of pages, this is not so easily done. So they needed to come up with something. And actually, what is happening here is they needed to not only run the page rank for each site, but also on the link side, so getting the score as an effect of what it's linking to. And in that sense, they want to run every site on internet, running the creating a page rank object for that. And then for every other site on the internet, they want also to check if it's linked to this page, and in that case, add the page rank from that site. And in the end, they want to have the current page rank. And thanks to nesting two loops on each other, you have the complexity of n squared, which is horrible for computing systems. So what to do instead? Maybe we can split it down into different languages. So maybe having one for English sites, one for Chinese sites, and some for German sites, and run those separately. But what if now they are linking each other, or if they're even multi-language sites, what happens? So what you really need to do is buy a really, really big and fast computer. But even on the most powerful computer today, one loop would take months to compute. And they want to update it at least daily, if not hourly. So this approach doesn't work. So they need to do something that is more efficient. Added to these problems, that you have this complexity, you have also what happens if one computer crashes. Do you have redundancy for that? Of course, you can always have a backup computer and running to replace it. You can also have, and that works actually for just a single, for small system, but if you have hundreds and thousands of computers, I mean, these computer centers, they have really many, many computers. And maybe what happens if there is an earthquake, which can happen in California. Google have their seat in Palo Alto, which is just in a good area for getting earthquakes. So what happens if their main computer goes down in the earthquake? The other thing is further on that PageRank doesn't only count, they do a lot of other metrics. And maybe you want to use old rankings for a page updates, and maybe you want to see some history in the whole thing. And then you may even want to run the PageRank several times to get it converting to something. So it's really a complicated system that they are working on. And what they did is to do a system based on a concept called map and reduce. And with that, you have two parts. You have a mapping part, so you have the input data, and you map it to some function. In this case, in this example here, the mapping function is the square of the value, and the output is something is then the squared of the input data. And the next one is that you want to reduce it, and our reduce function takes two arguments, and that would be a and b, a plus b, and that is reduction. So what we want to do in this example is to do the squared sum of the elements in this data vector. So what is happening in the reduce is we reduce each one step by step down here, and then we call the same function repeatedly. You can probably do the reducing in different ways. In this case, it's just called as a sequence, but you can also do them pairwise, and then you get more parallelizable. So I would actually organize it differently, and then so you would have, for example, G of 1 and 2 and G of 3 and 4, and you would reduce one operation actually. And then you can get into n log n of the number of operations instead. But that is what is happening, and this mapping part is easily parallelizable. You can just split up your data set and do it on as many computers as you want. Here you can set the reduce. You can also split out the reduce to several computers, and with that you have a way of doing it parallel. So the whole idea is you can partition your whole input data into chunks across the cluster, then apply map for each element. You need to do some reshuffle and repartition of the data, and then apply the reduce on each group, and then collect the results and write it to the disk. And usually the way of writing it is this tuple, where you have the data, you have the mapping, and you have the reduction. And that is the job that you submit to the computer. And you need to also reorganize it, so you have some key value pairs for the grouping. And the important thing is that the key must be comparable, so you can put it in sort it in some way, or at least group it in some good way. And the value is the information which is associated with that key. And the next, we want to count words. So for example, we have a sentence, a long array of words. And the first part is the mapping, where we split a string into words, and every word is mapped to the word itself and a 1. And this actually expands the data a little bit, because so that means that this word is counted 1 time. Then the regrouping is the next step. Then you would bunch every of the same word and create a vector of the ones for those. And now I need to scroll a bit. So, and then in the end we have the reduction, add up the values for each word, and here we have our 2 sentences. So we have the L vector is 2 strings, cat, dog, car, dog. And then we do the mapping of this. And what we come up with is that we have now a little bit longer list, where we have cat, 1, dog, 1, and so on. The shuffle and regroup counts, or actually produces arrays of ones so many times as you have it, and then in the end the reduction is summing all the ones you have for each of these elements. So that is the way how this map and reduce works. May look a bit overly complicated, but it is efficient if you distribute it on a larger system. And for that we have a word count example. Let's take Shakespeare's A Midsummer Night's Dream. I think the whole file is some 100 megabytes, but let's just read it in. There we have this data string, and we read it, and a long list of lines. So we get all the lines, and looking at the first 5 lines, we can see the initial lines of A Midsummer Night's Dream. And now we want to count these words. There is the way of doing it imperative with the serial selection, and that would look something like this, where it extracts every word and counts every occurrence of that word in a hash table. On my computer here, it took now 600 milliseconds, which is probably quite okay. And now to look at what it looks like when we do it with this map and reduce approach. First we want to see the analysis results. And we have the top list and the bottom list. And the top list is the expected suspects. But the least frequent ones are quite interesting words. I don't think I have heard many of those actually. So, so they are the strange ones in the type of English that Shakespeare used. Now let's go for the map and reduce approach. So what we need first is to create a little function, line to words, which is a mapping. And then we put in a string here, and out comes this list of words instead. And here, if you remember from last week, we also have this auto test. So that's a little unit test on this function that gives a test that the output is the right one. So now we need to use some efficient way of doing it. And there is something called DASK. And actually DASK has some a concept called DAGs. And that includes mapping, filter, folding, and grouping. And it can work also in parallel, splitting up the data in efficient ways on multiple cores and execute in parallel. And it can be iterating with lazy evaluation. And it can also allow larger than memory data in the operation. And it can also further on be done on a single machine or distributed. So it's really a multi-purpose tool, these task bugs. So what we need to do, a little bit of code, we need to first create or import the task bag and create an object from a sequence of all the lines. And we also tell that the partition size is 10,000. And that is it. And then we can see here that we get from the sequence, we get 13 partitions. The map output is using, we tell that we want to use the line to words function, and it should flatten the data. That's probably just a pre-processing in a way. And then we have the operation flatten after this, splitting up the data. Next step is finally to just map output and compute the frequencies. And that actually computes the histogram of all the words. And then from that we can get the top 10 and then we can get the bottom 10. And this took now 63 milliseconds instead. So it's actually a speed up of a factor 10. And I think that matches actually with how many cores I have in my computer. And then we want to run some diagnostics on it, trying with different number of workers. And from that, this one takes a little bit longer because it's a more doing some profiling metrics on the data. So this one took actually 2 seconds almost. And here is an example. You can also profile, see how the profile, what it looks like. And in my efforts of installing some missing details, I killed the bouquet package, which I couldn't reinstall, and I didn't dare to try to reinstall it and fix it, because usually fixing bad installations result in that I have to reinstall everything. So I just got a screenshot from what it looks like. But in principle, this DAG visualize can show the profiling results, where you can see the worker IDs and the time scale of when they are working. You can see these little pieces of the bars that tell what is actually going on in here. And you can also see the, oops, let's go up. No. Where am I? I'm lost. I don't see my mouse anymore. Whoops. So now it should work. And here you can see how the CPU is working, and you can also see the memory footprint of the operation. And apparently it is a memory consuming operation doing this mapping and reduction. So that is also something you need to be aware of when you do it, that there can be an expansion phase and a reduction phase. So typically the mapping does an expansion. Finally, no, not finally, but the next step is when we have all these parallel ideas, we need also environments for distributed computing, and one is the Hadoop, which is an open source version of MapReduce, and this is released as a part of the Apache project. And it allows that you have non-local data copied across the network, and then the storage is automatically expanded. And finally, it's actually what many of the big companies are using to deal with their big amounts of data. So Amazon, Microsoft, Yahoo, Facebook, etc. They use Hadoop in the backend of their systems. So it is well tested. So all these companies, they're actually behind the consortium of providing the Hadoop. And then there is Spark, which is also one way to handle these DAGs, so directed acyclic graphs, which I'm going to show you a little bit later. And they can do also this MapReduce, and it does a lot of in-memory caching, so it's a little bit more efficient that way. And it can do all the distributed and parallel computing without extra compiling and handling it. So it's a more convenient way of working with. So you send the things to it, and then it manages what you want to. So what it's doing is, for example, the scheduling, that it doesn't tell one computer to wait for an image from computer 2 to perform an operation and send it to computer 1. It's trying to redirect it in a more efficient way. And then you can also store the data to the destination you want. If you want it redundant or not, that can also be specified what you would need. So that is also included in with Dask, that you have default torrent computing, you have robust distributed computing within it, and you can add that to numerical Python code. So it's a quite convenient thing. And the idea with Dask is actually that it have mirrored many functionality of NumPy and SciPy, and that makes it also easy to work with these libraries, because you just have to change the naming. So normally you have import NumPy as NP. If you do import dask.numpy as NP, then you have the parallel version. So it's really easy to replace. And they can also be used in Spark and Hadoop-like problems. So how does it work to do the computation in parallel using these? Mainly we do these DAGs, and here are a lot of different approaches to how to do it, and some you may have seen before, like TensorFlow is something we have done before. PyTorch is also one that is used a lot in machine learning. KNIME is a graphical user interface where you can more or less, with small boxes and lines between, can program up your analysis. Personally, I don't like that kind of programming. It can easily get messy. spaghetti code in its wordly sense, because these graphs can be quite nested. And but it's good in the beginning to understand how your things are hanging together. And another thing is when you want to optimize your code, you can of course do it manually, that you try and tweak and recompile or reshuffle the code. But there is this a Facebook coding example where they actually permute the code, the same code more or less, but it's algorithmically permuted, and they have different generations of the code and see which one is executing the fastest. And then they see, okay, there are two alternatives which are the most relevant, and these are again permuted into new versions of a code, and in the end you can in that way get the most efficient code for your execution. And here you see the fastest one is 67, and now in this permutation it was 42, and here it ends up with, the fastest kernel that was computed was 42 microseconds. And well, 42 microseconds may not seem a lot, but if you want to repeat that many times, then it makes sense. You can see the first one was actually 187. So it's a speed up of a little bit more than 4. So that's a quite good improvement. So I said that we could take the code from NumPy and bring it into Dask and getting parallel code. And that can be done in this way. So import Dask array, which would be the same as the NumPy array. And then we also have the Dask dots, which is a graphical representation. Not really needed, but it looks nice. And here we create two images. One is image 1, which is a 5x5 and a chunk of 5x5. So that means this image is only processed as one single block. Then we create another one, image 2, which is then only once in a 5x5 matrix. And finally, I want to show it, and this is where the dot graph comes in. I want to show it, and the graph of that DAG looks like. So it's only creating one single image. So this is not very exciting as such. Now, if we want to compute something with these, so we want to compute this equation. We have image 4 is the same, is equal to image 1 minus 10 and image 2 times 50, and the sum of those. Then you can see the graph that comes out of it. Looks like this. So you have your input data, you have multiplication with something, and then you have subtraction here, and finally you add. And this looks like the way you write it is actually like a normal arithmetic expression, but it's not yet computed. You have to tell it to execute. So this is the lazy execution way. And here is another one where we do a matrix multiplication, two images and here you take image 1 multiplied by image 4, and you get this graph out of it. And it's still not computed, but you see here that it remembers that image 4 was actually the combination of this one, and then we want to multiply it by that one. And finally, we get some result. So, how can we do image processing on this? Again, now we import the Dask array. We have image read, and that's actually all we do right now. We just read the data and that's just reading and still. So reading and showing. So we have a volume of I think it was 250 times 400, 400 or something, but we extract a smaller volume out of it. And here you see the sum of all frames, and here you can see 10 frames, selected every 10 frames or something. So let's create DAG with this foam image. And yeah, it was 100, 400, 400, okay. And we want now to chunk it up into 20 slices per chunk, and scale the intensities, which from the input image was between 0 and 255, and we want to scale it in between 0 and 1. And so now we do DA foam. So we take the DASK array from the NumPy array, which is divided by 255, and we say that we want chunks of 20 in one direction and 400, 400. So now we have we get 5 chunks of the foam image, and then it looks like this. So we have chunk 1, 2, 3, and 4. And in this one, we want to now apply a Gaussian filter, the Gaussian filter comes from DA and DFilt, and it has the same syntax as the SciPy image, with different sigmas apparently here. So with 3, 6, 6, so we do less filtering in the depth than we do on the slices. And this looks a bit more complicated. Do you know why? Could you imagine why it would be more complicated than just writing each filtering as it is? So what is happening is that when you apply a filter and coming to the edges, there is an overlap. You need to know what's happening beyond the edge. And that is what is happening here, that it's creating an overlap region. And in this overlap region, you get the edge information. And when you go beyond the margin, you need to fetch from another image, from another chunk. And that is the information you need to blend in. And that is why this code also is looking so complicated. And now we want to apply a threshold on that, and also erode with the structure element of radius 12. And that even looks even more ugly. But you can see here, you have the filtering part for the Gaussian filter. And then there is a little bit of trimming, and then you do the thresholding, comes here. That's an easy one because it's pixel by pixel. And then again, when you do the erosion, then again you have to expand it and taking the overlap code to finally get your result. And this communication between the chunks is possible, but that is actually the point where you need to be careful that you not overwrite and do the wrong things. And if you would work with a distributed system, that would be the interaction between the nodes of your system, that they need to talk to each other to get the margin information. So that can actually slow down your processing when you go in a larger system. But this is handled automatically, but you have to be aware that you have larger kernels, then there is also much communication between the nodes. And then we want to also label the images, and we want to have labels which are globally unique. So you can't have that you have the same label in different chunks. Otherwise it would look quite strange. And then we run this labeling DAG, and the result is first, if you don't take care of the overlap, you see that everything gets, each chunk gets its own color, which is not what we want. So there you need to make some smart code to make sure that the labeling is actually happening in the right way. Another thing is the importance of order of operation. If you want to filter, you want to have a filter slice out of the data. Depends on how you do it. You can, in one way, do select a slice and filter it. And the other way would be to filter the whole image and select a slice. And of course, this one will take much more time. It could be that you need, that you need to do the full 3D, but you need to be aware that it takes a lot more time in that case. The reason to want it is that you want to have a 3-dimensional filter, and then you actually need to have the whole stack filtered. But if you only want to filter a 2D slice, then it's fine to run it like this. And here you can see the difference of running the two. The result is the same, but doing it single slice filtering takes half the time of doing it the whole volume. Considering the size of the image, this is not a big difference, but that's probably related to the overhead that is needed for calling the different functions. So what's happening is, you can see here, if you just select a single slice, you have a very simple structure. If you want to filter the whole image, then you kick off the whole big machine with a lot of overlapping and things. So I'm actually impressed that that one was so much faster still, but the reason is probably that the parallel code kicked in and did magic. So cloud computing is, of course, local resources is a problem that if you occasionally do some computing, which is heavy, having a local computer requires that you have, first of all, you buy the computer. The second is also that you have to maintain it, which also costs money. And mostly it's just standing around because you can't use it to 100%. So it's in a way inefficient, but you are the only user on it. If you use cloud resources, there is a lot of automatism built in, and the unlimited potential is available if you pay for it, of course. And also the whole setup and maintenance is handled by someone else. Even more is, I don't think I have it on another slide. No, I don't. Hey, come on, back. Another thing is also buying a computer, say with sufficient much memory and sufficient number of cores to do a calculation, costs quite a lot. But buying some minutes, hours on these clouds costs a few bucks, and that's it. So you can really do a lot of speed up with little money if you go to, for example, the Amazon cloud. So there's a lot of tools available in some of these infrastructures. There are, for example, k-means in a nice parallelized way, matrix factorization, graph analytics, machine learning. All that is already available on these clouds, so you don't have to do much. And there are many companies doing it. And the Spark is a platform which is used for these computational systems. And it is actually open source, so all the source for the Spark system is available. And there are no patents and restriction in using. And if you want to, that one actually is a very old line. I don't know if it's true. Was my predecessor, so, but I would say that it's still in use, so they probably still use it. And So beyond this, what we have talked about now, there is streaming as an option. You can do a lot of processing, maybe in weeks instead of months. You can also sometimes do real-time analysis and statistics. So streaming means that you do the acquisition, and just after the acquisition you do the processing, and that speeds up the whole processing, and you have better data from the beginning. So to do that in an efficient way, you need to add more computers all the time, and just start workers on the computers to get your things running. Another thing that is relevant to think about is if you have really, really much data, then it takes too long time to get the result, all result, and then you can set kind of a limit that you want the result within, say, 5 seconds. And the result you get in 5 seconds is for you enough for your calculation, so to get a quick idea of your results. Or you can also have some correction. So this is probably the CI, what is it? So probably some convergence index that is converged to 95%. You can see from the convergence of the calculation that when you have reached 95%, then you can trust that the result is quite reliable. The final result may take a couple of weeks more, but you can get this in some days maybe. So that is also a good way to do. And often when you do web searches, this is what they're doing. They actually put a constraint that within a limited time you get a result. Maybe not be the absolute perfect result, but it is a result. Yeah, and that was the end of this lecture and also of all lectures. And the summary is more or less that you can do more if you go parallel. It's not always trivial to go parallel, but there are also tools to work with. And still, if you go parallel, the resources are limited, and sometimes you can get into redundancy and race condition problems. And well, with the DAGs, you have a means of getting parallel code, parallel processing done, without even see that you have threads, and not at least directly. So that makes it convenient. Otherwise, you have to go down and really. So if you would do multi-threaded programming in, for example, C, you have a lot of coding mess to take care of. But with the DAGs, you just specify how to chunk up your data and then send it on to the system. Yep, that was all. And just a last thing I have. Where is my mouse now? I lost my mouse. Ah, there it is. Ah, found it. I also did a little summing up. Oh, date is not updated. So this is just a little quick overview. Why QBI? So quantitative big imaging. So we have a lot of data and great amount of data, limited time and limited manpower, and we want to do the most useful information of it. And that means we want to publish some quantity analysis, making it reliable and repeatable. And for that, we want efficient automated workflows. And for that, we need to understand how the data is created, image processing tools and analysis methods, how to work with the data, and also, as we did today, some computer science and computer engineering is needed also to manage it in a good way. And finally, how to present the results in a way that it makes sense to also to the readers, not only to you. So the workflow goes through that we get our data, we maybe even work with other people's data set, we do some filtering, then we do segmentation, more advanced segmentation, some shape analysis, and from that we can do clustering and conclusions. Then we go on looking at the statistics of the data, also looking at the uncertainties. Then some specific applications are time series data and multimodal data, which produces even more data, and also maybe some other ideas how you work with it. And finally, when we have a lot of data, we should go towards parallel processing systems, and that is more or less the overview of what we have done this spring. And well, this is just the lectures, some interesting bullet points for each data or each lecture, and yeah, so those you can just browse through in the notebook. And yes, that was the last one I wanted to see now. So again, to the project. There are some ideas about what this project is about. So we should have some kind of scientifically driven project, not just count the number of bubbles. That's as such a little bit boring, but more seeing what is the effect of some change in the system and make a conclusion out of that. And that means you need to take your images through some appropriate steps in the analysis, and maybe even characterize parameter space and error sources. And after the project, we will have a short presentation on 1st of June, and that is the last occasion. Actually, the next weeks until that date, there are no lecture time, but it's more consulting time. And the presentation, I don't know how many will do a presentation, but looking at the number of people in the room, you can have more than 5 or 10 minutes if you want, where you then show define your problem, showing your resolution, and tell your key findings of that. And there are some overview of some projects, and here I have some examples. One is performance analysis of sphere packings. It's a project I have started myself. I did a lot of tomographies, different exposure times, and I want to know different limitations of different acquisition conditions, and see how the processing can improve the output quality of the segmentation, for example. And this is looking at resolution boundaries, etc. Another one is fault evaluation in additive manufacturing, where we have some tomographies of metal parts with some geometric structure, but it was not done perfectly, so there are some faults in it, and the question is where these faults are located, and the sizes as function of distance, for example. Another one which has been done for quite many years now is detection and analysis of calcification in breast mammographies. And then there is a whole bunch of other projects which relates more to different Kaggle exercises, many developed by Kevin Marder, who taught this class before me. And there are some different looking at the running analysis on video, could look identify whales, heart rate, heart ejection fraction. Yeah, looking at digit recognizers. Yeah, so there are some different ones, or of course, so that gives you an idea. Otherwise, of course, if you have your own projects, you're welcome to come and discuss them with me. Either just now or also you can just send me an email, preferably to my PSI address. And I do have a link to sign up. Just have to check if that is the right one now. No, it's not. It's the old one. Didn't update. Okay. Then better send me an email and I'll take you up in the list. So, thank you. Yes? Yeah. Uh-huh. The exam is an oral exam, and well, there's allocated 30 minutes, but usually it's more practically more like 25 minutes. And it will be like a discussion. I throw you sometimes some general questions, like describe how you can achieve that, and then while you describe it, I throw in specifying questions, etc. And if you get stuck, I try to guide you in the right spot or change topic, because I can't stop on the same thing infinitely long. So that is the way. And I do have some example questions listed that I could distribute. What was the question? Sorry.